Okay, so welcome back to class. The plan for today is to finish up section 3.2. That might take us most of the rest of the class, but I want to at least get a start on 3.3. Chapter 3 is really a pretty packed chapter, so there's a lot of material, which is why it's taking us so long to get through each one of these sections. And the material is fairly technical, so it's not the kind of stuff that we can just take a quick glance at and then move on. And the material is also quite important and foundational for stuff that's later in the course. So we're taking a little bit of time to get through chapter 3, but 3.3 is the last section in chapter 3. And after we finish 3.3, fingers crossed, hopefully we'll finish it up next class. After we finish 3.3, we'll be kind of shifting gears pretty substantially, moving into chapter 4 on probability. So looking at some more kind of theoretical groundwork. Also note that part of 3.1, we talked about measures of center. A couple of the measures of center that I mentioned were, important in certain contexts, were the geometric mean and harmonic mean. And just to save us a bit of time, I posted a supplement on the YouTube channel. So check out the YouTube playlist. I posted a supplement on the geometric mean and harmonic mean, just going through that material outside of class. So that way, if you read through it in the book and you're comfortable with it, you can just do the couple of homework problems on them and feel good about it. Or if you want a little bit extra direction, you could check out that supplemental video on YouTube. The quote of the day, kind of two quotes of the day related to one another. One of my favorite things to say or to think about myself is don't walk over dollars to pick up pennies. I see this sometimes in other people, and probably if I, looked in the mirror more often, I would see it in myself as well, that a lot of times people hyper optimize things that aren't really high yield, right? So like my mom loves getting sales, so she'll go to 3 different grocery stores to get this thing that's on a bit of a sale over there and that thing that's on a bit of a sale over there, and it's like, how much time and effort and even gas money or whatever does this cost you running to all these different places to, at the end of the day, you're not you're saving really that much money on it. Maybe these extreme couponers can save tons of money or whatever, um, but right, so it's kind of like, don't hyper optimize the small stuff at the cost of the big stuff. Now, if you enjoy getting the sales, I think that's half the reason she does it, is she just kind of likes finding all of the sales and running around and all that. And hey, if you're retired and you enjoy that, go for it. But don't do that at the cost of the higher yield stuff, right? Don't for instance, make a bad deal on buying a car because you didn't put the time into researching what the value of that car is and what are your options, and taking the time to go to a couple of different places, and this place didn't quite treat you right, so you just walk away. Don't sacrifice that deal that's a $15,000 or $20,000 deal, so that you can make it to your 3 grocery stores and save, an extra 12 cents on a can of beans or something like that, right? So this is really talking about trade-offs. Think of the trade-offs or think of the decisions that are high yield versus low yield, that are high impact versus low impact, and try to structure your trade-offs that way, right? Um, I'm more than happy to pay double what I should for an item that only costs $1, because the absolute scale is so small. If I overpay by $1, I'm not really worried. I really don't want to overpay by 2% on an item that costs $20,000, because that's hundreds of dollars, right? So the absolute scale is important as well. And I think that goes uh, for classwork as well, right? If you can study a little more for an exam and maintain your focus there, that exam might be higher yield than really grinding away and getting, that last 2 points on one homework problem that you're really struggling with, getting that right. If it takes you a half an hour to get that 2 points on one homework problem, versus if you spent that half an hour, say, studying for an exam instead, where's the higher yield, right? I mean, ideally, we would, pick up the dollars and the pennies, but we're all faced with trade-offs, time crunches and attention demands and all of that. So we have to make decisions where we spend our time, where we spend our money, and so on. Uh, so we need to focus on what's high yield. Uh, as kind of a little side note, I think it's kind of unfair almost that, if you look at it, the span of a person's life and you say, okay, what are the 10 like most important, most high yield decisions they're going to make in their life? More than half of them, I would say, come before you're 18 or certainly before you're 20. Um, that's kind of not really fair, right? You don't have very much life experience at all at that point, and you're really setting yourself up for success or failure in life in a significant way in those decisions that you make at a time where you don't have much life experience at all. So, um, but focus on the big picture items. Make sure that you make those big decisions well, and if a little decision here or there slips by you, that's not as big of a deal. Kind of a related idea is this is attributed to Carl Jung, so a psychologist or psychiatrist from the early 1900s, like kind of around the Freud time, maybe actually late 1800s, early 1900s, like roughly ballpark Freud time. So this quote's attributed to him. I don't think this quote is a direct translation of the German that he wrote in, but I think it's kind of a good idea that's, that kind of came out of his work. Um, and it goes something like that which we need the most will be found where we least want to look, right? We often like picking up pennies because it's kind of easy to do. We get a nice little dopamine rush, right? We like succeeded on something small, that feels good. Um, and maybe those pennies in a sense are where we're comfortable looking because we can solve those problems easily. But the problem that really needs solving is the problem that we don't want to look at. So I think that's a related idea. Okay. All right, so those were the thoughts for today. Okay, moving on to 3.2 measures variation. Uh, just a quick recap. Remember that the idea here, the kind of general question is something like how variable is the data set, or put another way, how far can a data point's value reasonably deviate from typical in this data set? We looked at the range last time, and the range is simply the difference in the sense of subtraction between the maximum minimum data value. So x max minus x min. Well, these probably should be capital X's to stay consistent with my previous notation, or xn minus x1 if we've put everything in order. The range has a couple of pros. It does give an estimate of variability. It's kind of saying how wide is the swath of the real line covered by the data, and it's obviously easy to compute. So that those are definitely pluses. It has some significant downsides, though, some significant cons. It only looks at the extremes and only at two data points, right? It only considers the values of two data points out of possibly hundreds or thousands of data points. So for instance, if I were to imagine, say, grade data for two different classes, here's 80, let's say 90, and 70, 60, and 100, and another class. Maybe I have one class where literally everybody in the class scored exactly 80%, right? If I have another class where, say, half of the class scored 60 and half of them scored 100, well, the mean is 80, right in the middle. These are two very different classes, right? If I looked at one versus the other, well, the mean is the same for the two, but the variance, or sorry, not the variance, the measure of variation, the range would be very different. Range is 0 versus range is what, 100 minus 60 is 40. This seems to be a pretty, this seems to make range look like a pretty reasonable measure. But if I were to just take two of these students and one got a 60 and one got 100 and everybody else in this class got an 80, well, now my ranges are actually the same. So even looking at a measure of center like the average, along with a measure of variation like the range, even the combination of those two wouldn't discriminate between these two very different data sets. This is basically a coin flip, whether you do great or fail. This one is like most students in this class did pretty well. Those are very different data sets. I would like a measure of variation that can discriminate between these two, that can take a look at every single data point. So that's what we're trying to do with the variance. Okay, so let's take a look at the variance and we will build it up from first principles. So what's the idea of the variance? Well, I want to look at, say, a data set, and I'm going to draw my data points just kind of like this. I'm going to draw them at different heights here so that I can illustrate something else later on. But this is just saying there's one data point at this value, there's one data point at this value, one here, 5, 6, and 7. So we have these, say, 7 data points. I can find the mean or a measure of center for these data points. Maybe it's something like here. Let's just call this X bar, or we can kind of imagine it being any measure of center, some typical value of a typical data point in this data set. Now, if I want to answer the question, how variable is the data set? Again, another way I could phrase that is how far can a data point's value reasonably deviate from the typical or from, say, a measure of center? So I might be interested in the deviations here. So I might be interested in the sizes of these red bars. So if I call this data point, let's say x1, again with the small x's, I don't know why I want to do small x's today. There's x4, x5, x6, and x7, for instance. And I might look at, this bar associated with x2, and I might say, okay, it's x2 minus x bar. Or with x6 being, say, x6 minus x bar being that distance. So I might look at the xi minus x bars. I might look over here at like x1 minus x bar or x7 minus x bar as well. So I might want to do something like somehow accumulate these xi minus x bars. So can I do something like add up x1 minus x bar plus x2 minus x bar and so on, plus, let's just say, xn minus x bar? Will this give me a measure of variation? Will this give me a number that kind of gets bigger the more spread out my data points tend to be, or the more they tend to be farther away from their mean or other measure of center? We're using the mean here, but as the example, or other measure of center. Well, what happens when I do this calculation? I see I can rearrange some things. I can actually put all the xi's together. I can add all of the x1, x2, and so on through xn first. And then to that, I'm going to subtract off, or from that, I'm going to subtract off x bar once and twice. I'm going to subtract off x bar n times. But what can I do here? Maybe you might see it already. You might already see that nx bar is just exactly what's in parentheses, but maybe I could make it a little clearer if I multiply by n over n in this first term, and I realize that I get nx bar minus nx bar. This turns out to be exactly 0, no matter where any of my data points are. Why is that? Well, the reason is that, say something like x6 minus x bar, x6 is bigger than x bar. This is a positive number, as is this one and this one. However, x7 minus x bar, because x7 is less than x bar, this is actually a negative number. And here, and this one. And it turns out that x bar is, um, kind of the measure that is such that when you add all of these deviations, they're not really deviations. When you add all these differences up, you end up with 0. Okay, so we kind of have the right visual idea, but the arithmetic or the algebra needs a little bit of work. We need to fix the algebra. So I like this idea where I say something along the lines of the bigger these red bars tend to be, the bigger my measure of variation should be, because my points tend to be farther away from the associated measure of center. My problem is that these bars or these calculations have signs on them. Some are positive, some are negative. So when I add them together, they kind of cancel out. I want them all to point in the same direction, so that whether a bar is far or whether a point is far off to the right or far off to the left, I'm looking at the length of the bar and combining them together in the same direction, so they're not canceling out. Now, one way that I could do this, maybe the first way you would think of, is to just slap absolute values on everything. If I just put absolute values on everything, that makes all of these positive. That is really just the length of that bar, that distance for each of the bars. And that actually works okay. So if we used the absolute value idea, and we probably want to combine it with the median instead of x bar for the reason that I touched on last time, that with that loss function, it's kind of like absolute value is the loss function associated with the median, but we might end up with something like the median absolute deviation from there. And that's an okay measure of variation. It has quite a few shortcomings, though. In particular, the absolute value function kind of has this annoying corner that makes some of the analysis, the kind of fundamental underlying analysis that we're not going to really get into, makes that a little bit more annoying. So there are some good reasons that we don't want to go this route. It's not that that's fundamentally a bad route to go. It's just that it's inconvenient, and a lot of the results that we'll see in our course, um, the fundamentals don't really work so nicely with this median and absolute value idea. So one way we could take a number that could be positive or negative and force it to be always positive is to absolute value it. But we don't really want to do that. Another way that we could take a number that could be positive or could be negative and force it to be positive is we could square it. And that's what we're going to choose to do here. If you remember, the loss function related to quadratic loss, the squaring idea, is the one that's related to the mean, the average x bar. So I'm going to choose to take each of these and square them. Oops. This one squared. That's going to turn each of these negatives into a positive or a non-negative. If I say positive, I really just mean non-negative. It could be 0 if the data value was right at the mean. And of course, if I square a positive, it just stays positive. So this is the approach we're going to take. We're going to choose to take these xi minus the means and then square them to make them all non-negative, or basically make them all positive, and then add those together. That's my measure of variation idea. And I think this is going to work a lot better. We don't have any cancellation anymore because everything is coming in as 0 or positive. So everything is adding together in the same direction. This is not going to be 0 unless we were in the very strange case where every single data point had exactly the same data value. But for all intents and purposes, for any reasonable situation, this will not be 0. We're not going to get cancellation here. We do have one more kind of annoying thing, though. Well, if I have say a population, I take a sample of size 10 and I take a sample of size 1,000, I mean, that population has itself a measure of variation, maybe a population variance, a parameter. The whole idea of of getting sample statistics is to estimate that population parameter. But if I add up 10 positive things, or if I add up 1,000 positive things, the 1,000 positive things are usually going to be bigger than the 10 positive things just by nature of there being more of them. So what would tend to happen here is as n increases, the variance increases. That seems kind of strange, right? That just by nature of me taking a larger sample, I'm saying that I think that my population is more variable. Well, that shouldn't be the case. I should expect that as I take a larger sample, my estimate of the variance of the population gets closer to the actual variance of the population. Not that it should just, keep growing. So really what I want to do is I want to factor out in a sense the size of the sample, and I do that by dividing by n. And I am being a little bit careless here. There are some details we're going to clean up in a few minutes here. But this is the idea of our variance. So what is the variance? It's a deviation from the mean. But squared. So it's a deviation from the mean that gets squared, and it's something like the average of that. So in words, what is the variance? The variance is more or less the average squared deviation from the mean. We notice that this does touch every data point. All of the x1s through xn's are explicitly listed in this formula. And it's a number that's going to get bigger the farther my data points tend to be from the mean. That's exactly what I'm looking for. This can certainly discriminate between, I erased them, but between those two scenarios where I had a bunch of data right in the middle and only a couple of data points out at the ends, there's going to be a couple of big bars. Variance won't be all that big, versus the data set where basically all of the data points were quite far from the mean. Every single one of those data points is going to be contributing a big bar, a big term here, and that variance is going to be much larger. Okay, so let's look at the details. We do have a couple of details here. So notation. So for the notation for the variance, for population variance, is this letter. This is Greek lowercase sigma, Greek lowercase s. It's the Greek s that comes in the middle of the word. The s that comes at the end of the word looks like that, which is obviously the one that's related to our s. But this sigma is like the lowercase s that would come in the middle of the word if it wasn't the last character. You might also be familiar with capital sigma, the summation symbol. That's the capital letter associated with this lowercase letter. So our population variance is sigma with a superscript 2. Now, something important to note here is that this is a notation. It obviously has that superscript 2 taking inspiration from the fact that we're squaring the deviations from the mean. That is certainly related to this. But this is not saying that we like do whatever calculation follows to get an answer and then square it or something like that. Sigma squared is the notation that means population variance. So sigma squared equals the population variance. We also have a sample variance, and kind of in correspondence with the mean, population versus sample mean, S squared, or S superscript 2, I usually just call it S squared. That is a notation. That's the sample variance. Okay, so how do we compute sigma squared? The population variance? It is exactly what we wrote up here. Well, almost exactly. I mean, I used X bar up here, but because we're in a population, we're going to use mu. So it's x1 minus mu squared plus x2 minus mu squared, and so on to xn minus mu squared, all divided by n. Now, often you'll see books writing this as something like capital sigma xi minus mu squared all over n. And that's a more concise notation, but it's much easier to mess up. Some students will add up all of the xi's, subtract mu once, and then square the result. Some students will add up all of the xi minus mu's, get 0, and then square it and get 0, right? So I like to write the details out. There are a couple points in this course that I do use sigma notation, but only when it's really essentially necessary to make the point clear. Sometimes the writing everything out in long form adds so much complexity to it that it's hard to make heads or tails of what's going on. But here it's not too bad. So the population variance is simply the average squared deviation from the mean. What about sample variance? It turns out sample variance is calculated a similar but slightly different way. Nicely enough, our numerator is, for all intents and purposes, exactly the same, except that we're going to use the notation x bar to represent the mean here because we're in a sample. And here we'd really want to divide by n and call it a day. We have a bit of a challenge though. If we think all the way back to chapter 1, let me get rid of that n. If we think all the way back to chapter 1, we talked about different types of bias, and one of the examples of bias was estimator bias. And we said, for instance, if I was trying to estimate mu by x bar, and I computed x bar in some silly way, it probably wouldn't be a good estimate of mu. That might introduce some estimator bias. But it turned out that if I just, roughly speaking, compute x bar the same way that I would compute mu with the same formula, that's an unbiased estimate. That works as we would expect. We'd think that if I compute s squared essentially the same way I compute sigma squared, I should get an unbiased estimator of sigma, or sigma squared, but it turns out that doesn't work. So for our sample variance, we need to divide by n minus 1 to get an unbiased estimator. The exact details of why this has to happen are beyond the scope of this course, but I'll post a supplemental PDF on Blackboard that's called Why Divide by N minus 1 to kind of give you an illustrative example that if we try to divide by n with an s squared, our estimate isn't quite right. And if we divide by n minus 1, it does end up spot on. So I'll work through an example there, or you can, there's a good Wikipedia page on this that kind of explains more of the background, but it requires quite a bit more background than we have in this class. Okay, now if we look at this, we can see that this is by far the most challenging calculation we've done so far. We need to compute a bunch of differences, square each of them, add them all together, divide by n. So the way that I like to approach this is to write out my data set in tabular form and use the table to help me out. So let's take a look at the Ashley data. And let's try to compute the variance, the population variance for the Ashley data. Remember that this is a population. It's a population because we're told that it's a population. In other words, whatever statements we want to make about this data set, we're only making about this data set. We're not trying to, guess what Ashley's performance was over the span of a year based on these 5 days or something like that. We're only looking to describe what happened on these 5 days. Okay, so I'm going to start out by listing out my data points in a grid. So I have I and xi. So when I is 1, x1 is 5. So I is just the index, x1, x2, x3, x4, x5. I'll put them in order, 5, 7, 8, 9, and 11. So this is my list of my data. That's my data set. And actually, if I take the time to list my data this way, this makes, say, computing the mean easy. I can just add up the numbers in this column. And then, not x bar, mu. Mu is going to be 40 over, and I can see I've indexed this carefully. So I know that n equals 5. Right. So I can get my mean fairly quickly. I can get my median quickly because everything is lined up. So if I do the work of arranging the data in a table like this, it even helps me for some of the previous work that I've done, right? I can find x min and x max very easily, just when I equals 1 and I equals 5 in this case, 5 and 11. But here I know that mu is 8. And what I'm going to do is I'm going to build off of this table that where I've drawn out my data set. I'm going to add a column to the right. So here maybe I'll actually do this in green. I don't want the blue to get confused with the blue that I was writing up there for the sample variance. So here, if I look at my population variance, the first thing I need to do is what's inside of all the parentheses. I need to find each deviation from the mean. Then I need to square it. Then I need to add it together. That gets me the numerator, and then divide by n to get my variance. So I first need to compute xi minus mu. Or for the first row, that's going to be 5 minus 8 is -3. 7 minus 8 is -1. 8 minus 8 is 0. 9 minus 8 is +1. 11 minus 8 is +3. One check that I can do actually is to see if I add this column together. Remember, that's just adding the xi minus mu's. That was the thing that should have ended up as 0. If I add this column together, do I get 0? Yes, I do. That's a good check, right? I get -4 plus 4 ends up being 0. Sometimes if I'm rounding, I might get, a little bit different than 0, but I shouldn't get far off of 0. Okay, so now I have my xi minus mu's. I need to square them. So I take -3 and square it, that becomes a positive 9. -1 squared is positive 1, 0, 1, and 9. So I just square each of the numbers in the previous column to get this column. These numbers in this rightmost column, 9, 1, 0, 1, 9, represent each of the terms, x1 minus mu all squared, x2 minus mu all squared, etc. To construct my numerator, I just need to go through and add them together. So what's the sum of these? The sum is 20. This is the numerator. Or sometimes it's the sometimes it's referred to as the SSD, the sum of the squared deviations from the mean. And then what's my population variance, sigma squared? It's just this numerator over n, the sample size, or the population size. Sigma squared is 20 divided by 5. 5 is the size of the population, or 4. Any questions on this? All right, let's look at the Brandon data. Let's do another example. So we'll follow exactly the same process. You can follow along with me. So first I'll organize it into a table. And note, just note that this is a table. It's not a frequency distribution, right? Frequency distribution was what we were talking about in chapter 2. That was a different use of a table. This is just the table to organize the data in the data set. So this, not a frequency distribution. Don't mix up those two ideas. And again, for the Brandon data from previous work, or I could compute it pretty quickly, I know that mu is 8. Brandon actually happen to have the same mean. And again, sigma squared is x1 minus mu squared out through, in this case, x5 minus mu squared over 5. So I need each of my xi minus mu's. So I'll append a table to a column to the right of my table, xi minus mu, that's 3 minus 8, or -5, 5 minus 8, -3, 7 minus 8, -1, 11 minus 8, +3, 14 minus 8, +6. So I have -9 plus 9, that sums to 0. That's a nice little check to do. So the sum of my deviations themselves turn out to be 0, as I expect. The next thing we need to do is finish off each term by squaring each of these deviations. -5 squared, +25. -3 squared is 9, 1, 9, and 6 squared is 36. So this rightmost column, 25, 9, 1, 9, 36, represents each of the terms that are being added together in the numerator. So now I just add them together. I get their sum. So what, 25 plus 10 is 35, plus 9 is what, 44, and plus 6 is 50, plus 3 is 80. I did all of my ciphering correctly. So the sum should be 80. And that's my numerator, aka my sum of the squared deviations from the mean, SSD. And then my variance, my population variance, sigma squared, in this case for Brandon, we can put a little subscript for Ashley up here. Sigma squared for Brandon is going to be 80 divided by n divided by the population size of 5. And that is 16. Okay. Any questions so far? So it's a lot of calculation to do, a lot of things to be done. But each one of them is pretty straightforward. And as long as we keep the overall strategy in mind, and I think the table helps a lot with that, if we keep the overall strategy in mind and importantly, keep the order of operations sorted out properly, I don't think I don't think it's that difficult. It's complex. There's a lot of moving parts. There's a lot of details that we have to do correctly, but I don't think it's that conceptually challenging. Um, the first couple of times you do it, it's going to be a lot of looking back and forth and wait, what was that next column supposed to be, or what was the definition? But after the fourth or fifth time you do it, it's more tedious than complex or complicated or difficult. Okay, so let's look at the units. I'm going to do units in blue. My XIs are in returns per day, and my mean is also in returns per day. So xi minus mu is in returns per day minus returns per day. These are in returns per day in this column. So all of these numbers, -3 returns per day, -1 return per day, 0 returns per day, etc. What happens when I square a number with a unit attached? If I have, 1 inch squared, that turns out to be 1 square inch, or maybe 2 inches squared turns out to be 4 square inches. So I square my number, -3 to 9. My unit also gets squared, returns per day squared. I add these up. These are all in the same unit, returns per day squared, to get my numerator, 20 returns per day squared. I divide by a counting number that's unitless, 5. And I see something really unfortunate here. That my variance, as nice as it was to get the number 4 out, I don't know what the heck this unit is. What is a return per day squared? There's a sense in which this is almost like a nonsense number because it's attached to a unit, which makes no sense. Well, no sense in general here, but at least no sense in the context of the data that we're measuring. So even if I was measuring things in inches and I got square inches out, I'd say, okay, I kind of know what square inches is. But if the data are measuring length, how does area relate to the characteristic we're measuring, length? That's not very clear. So even if I got a square unit out that I might recognize from another context, it's still kind of meaningless in this context. We have the same units down here. Brandon's population variance is 16 returns per day squared. Not really, uh, not really meaningful or easy to interpret. So the variance has some benefits. In particular, there are a lot of nice mathematical properties that relate to the variance. So things like under some circumstances, the variance of the sum of two random variables is the sum of the variances of the random variables. Things like that work really nicely for the variance. But practically speaking, if I report a number to you as a descriptive statistic that's the variance, it's kind of difficult to interpret because it carries these units that are square units. I don't really know how to interpret this number. So enter the standard deviation. The standard deviation, population standard deviation gets the notation Greek letter sigma. Given the two notations, sigma squared versus sigma, you might even guess the relationship between standard deviation and variance, especially considering the fact that we know that having a square unit is problematic. To get from population variance to population standard deviation, we simply square root. So the standard deviation for Ashley is the square root of, what was her population variance? 4 returns per day squared. We square root the number, that gives us 2. We square root the unit, that gives us returns per day. That's a much more sensible number to report as a descriptive measure. It has units of the original data, it has units that are sensible. What's Brandon's population standard deviation? We do the same operation. Square root Brandon's population variance, 16 returns per day squared. We square root the number, 16 comes down to 4. Returns per day squared comes out of the square root as just returns per day. Again, we're back in a sensible unit and units of the original data. So if I'm going to report a number as a descriptive measure, I would much rather report the standard deviation than the variance because the units match up. It's much easier to interpret. If I was going to do mathematical work with one of these two, I'd probably rather use the variance because the mathematical properties work a lot nicer with the variance than the standard deviation. So each of them kind of, has their place. But since we're in chapter 3 talking about numerical descriptive measures, the standard deviation is the one that we would prefer in this sense when we're trying to take a data set, report one number that says in some sense how variable is the data set or how far can a data point kind of deviate from the mean, reasonably speaking. So we prefer to report the standard deviation over the variance. It has units of the original data, and it's going to be easier to interpret for that reason. Okay, let's take a look at the salary data. I'm going to go all the way up here and grab the salary data. Sorry if I'm making you seasick scrolling so much. And remember the formula for sample variance, remember the salary is a sample data set. We're taking it to be a sample data set. The numerator actually is exactly the same. Well, aside from the notational difference, mu versus x bar, but we do the same thing. We find the mean, we compute deviations from the mean, we square them, we add them together. This numerator is still just the same SSD, aside from just that notational difference. Really, the only calculation difference comes in dividing by n-1. Everything we did in our table for Ashley or Brandon was with the goal of computing the SSD, the numerator. The table looks exactly the same between population variance and sample variance. Right? The difference comes whenever we decide what to divide by here, what we put underneath the numerator. Do we put n or n-1? That's where the difference comes in. So nicely enough, we can use this exact same table setup with just that minor notational difference to compute our salary variance. Let me get the standard deviation title back up where it belongs. There we go. Okay, so let's look at our salary data. Again, we'll start off a table with an index column and our data. We have 7 data points, 25. Again, if we have multiple data points that have the same data value, we include them multiple times. So I do 28, 28, 28. I don't like write down 128 and skip the others, anything like that. I make sure I have those 3 28s all accounted for. 30, 55, and 100. In the past, we had computed that X bar for the salary data was 42. All of these are in units of thousands of dollars. And now I'll compute Xi minus X bar. And since it's too early in the morning for me to think too hard, let me rearrange my windows over here and bring up my calculator. Go. Okay, so in my calculator, I want to do 25 minus 42, negative 17. 28 minus 42, negative 14. I have 3 of those. 30 minus 42 is negative 12. I can see that because I took the time to order these, I know that going from 28 to 30 just gets 2 units closer to 42, so my deviation just gets 2 units closer to 0. 55 minus 42 is positive 13, and 100 minus 42 is positive 58. Let's check this column and make sure it sums to 0. So I need 17 plus 14 times 3 plus 12. So I get a total of negative 71, and 13 plus 58. I get a total of positive 71. Those are going to add to exactly 0. So that's a nice little check that I did everything correctly. Right, if I had computed my X bar incorrectly, or if I had computed any one of these entries in this column incorrectly, I would get a sum that's not 0. Maybe if I computed 2 of them incorrectly, they might offset one another, but that would be pretty unlikely. And again, if X bar was rounded, if it turned out that X bar was like 41 2/3 and I made it about 41.7, then my sum is probably not going to be exactly 0, but it might be like positive 0.3 or negative 0.1 or something like that. But it's going to be pretty close to 0 on this scale. But here my sum turned out to be exactly 0 because nothing is rounded. Okay, so these are my Xi minus X bars. These are my deviations from the mean. I then need to square and then add together. So I take each of the entries in the previous column, square them. When I enter into the calculator, I don't need to enter the negative. I might as well just do like 17 squared, and just up and to the left of the 7 button on the TI-83 or 84 is the squared button. So you can just use that. Or you can use caret 2. You can use, to the second power. But there's a nice little special button for squaring, just this little x squared button there. So 289. 289. Let me make sure that looks like a 9. What is 14 squared? That is 196. I have 3 of those. 12 squared is 144. 13 squared is 169. I know those two. 58 squared, I definitely don't know. 3364. These are all of my xi minus x bar squareds. These are all of my individual terms in the numerator. I've got to add them together and then divide by some number. So let me add these. I need 289 plus 3 lots of 196, 3 times 196, plus 144, plus 169. Make sure I got all those right. 289, 3, 196, 144, 169, and 3364. Looks good. This gives me 4554. That's the sum. That's my numerator slash SSD, the sum of the squared deviations from the mean. And now to compute the sample variance, S squared, I take 4554 divided by, and here I'm not going to write 7. I'm going to do n minus 1, 7 minus 1, or 6. One note, I do not want to do 4 or 5. Oh, wrong screen. Let me jump over to the calculator. I do not want to do 4554 over 7 minus 1 like this. This is going to take 4554, divide it by 7, get that answer, then subtract 1. We're not going to get the right answer. We want to do 4554 over 6. That's going to give us 759, the right answer. Or we could do 4554 over parentheses 7 minus 1. That gives us the same answer. Be just really careful with your order of operations and all the details. The arithmetic details is where calculations like this are likely to go wrong. So 4554 over 6 gives me 759. So my sample variance for the salary data is 759. And again, this is in wonky units. This is in $1,000 squared, or millions of square dollars. That doesn't really make any sense. But that is what the sample variance is for the salary data. The sample standard deviation, you probably can guess, has the notation simply S. It's a wonky looking S. The sample standard deviation is denoted just S, and it is the square root of S squared. It's the square root of the sample variance. So for the salary data, the sample standard deviation is simply the square root of 759, and our units are thousands of dollars squared. And to get this answer, we square root the number 759. I can do second x squared to bring in a square root operator. And if I do second negative sign down here near enter, that puts in answer A and S, refers to the previous answer. Or I could just type in 759 if I didn't want to deal with that. And that gives me about 27.5. So the numerical part comes out to be about 27.5. And the unit now, we're back in reasonable units, thousands of dollars. So the sample standard deviation is about $27,500. Any questions so far? Okay.
I have a little doubt.
Yeah.
I missed that part. Where do we use divide by n and where do we use divide by n minus 1?
Yeah. Yeah. Good question. Uh, so when we have a population, that's when we divide by n. And when we have a sample, that's when we divide by n minus 1. And the sample goes with the s or s squared notation. Population goes with the sigma or sigma squared notation.
Okay, thank you, got it.
Yeah, sure. Yeah, something this is kind of a minor point. Um, when n is large, the difference between dividing by, say, 3 or dividing by 2 is a big difference, right? Say 1/3 versus 1/2 is like quite a bit different. But the difference between like dividing by 100 versus 99, it's not all that different. So actually, when you have a large sample, and the difference between using n or n minus 1, that that bias is going to get smaller and smaller the larger the sample you have. So probably if you have a sample above size 30 or something, practically speaking, it probably doesn't matter all that much. Certainly if you have a sample in the number that's numbering in the hundreds or thousands or something, it's not going to matter really effectively at all. But for smaller samples, the n versus n minus 1 will make a pretty uh, substantive difference in the answer. Yeah. Okay, let's take a look at the effect of outliers on variance and standard deviation. So we kind of looked at this salary data and we said, just with our just underlying understanding, subjective understanding of outliers, we'd probably say that 100 is an outlier and 55 might be. And looking at the way the measures of center lined up, that also kind of indicated there was probably a right outlier. So we pluck this 100 out and say the 100 is almost certainly an outlier. The 55 maybe. So 100's an outlier, maybe the 55. If we look at the contributions to the variance, basically all of the contributions are a couple hundred, goofy units of square $1,000 or whatever, millions of square dollars, whatever you want to call it. But they're on the order of a couple hundred, between 100 and 300. And then we see the outlier here. It's like a full order of magnitude larger. It's 3,000 something. Everything else is like 100 to 300, and the outlier's contribution is like 3,000. Why is that? This square is really actually doing a lot here. If we think of of a quadratic function, if we get, say, twice as far away from 0, xi minus x bar, the 0 point would be the data value sitting right at the mean. So if we get, say, twice the deviation, the output is actually 4 times as big. Or if we get 10 times the deviation, the output is going to be 100 times as big because we're passing through the square function. Choosing the square loss function, so to speak, penalizes, in a sense, large deviations much more heavily than small ones. So outliers have an outsized effect on variance and standard deviation. If you have the presence of an outlier or two, your variance and standard deviation are going to go up, uh, in some sense, disproportionately to the size of that outlier. So making this choice all the way back up here when we made the choice to use squares, filters all the way down and says, okay, well, now if you have an outlier, that gets penalized by this square function much more heavily than non-outliers. Penalized, I mean, it's not really a penalty. We're not like, paying $1 for each point of variance or something, but I think you see what I mean. The contribution to the variance from outliers is quite significant. So if we have outliers, they're going to really dominate uh, the discussion in terms of variance and standard deviation. Let's jump over to Excel. Let me stop my share here. I'm going to pop two Excel files in chat. So there's one that says Math165 Chapter 3 Demo. If you want to open that one, it should be in chat now. I'm going to open it and then share my screen in just a second here. Just getting my windows sorted out. I always have to close my Excel file before I can pop it into chat. Otherwise, Zoom doesn't like to share it. So, okay. So we have our data sets here, and here are our measures of center. And let's go ahead and compute the range, variance, and standard deviation for each of these three data sets. I did this again after class last time, so I renamed these Ashley, Brandon, and Salary for the names of the data sets. So you can see, for instance, for the mean, we have equals average of Ashley, or for the mid-range of the salary data, we have max of salary plus min of salary over 2, with parentheses in the appropriate place to keep the numerator all together. So what about the range? Well, the range, remember, all the way back at the beginning, is just the difference between the max and min value. It's kind of feels a little bit like the mid-range in the sense that it only looks at the extreme values, but where the mid-range is the average of the extremes, x max plus x min over 2, the range is the difference of the extremes. It's the swath of the real line covered by the data. So range is going to equal max of the Ashley data minus min of the Ashley data. So we're using the same max and min functions we use for the mid-range, but using them in a different way. We're subtracting them. So Ashley's range was 6. The range for the Brandon data, max of Brandon minus min of Brandon. Brandon's range was 11. And remember, the range is in units of the original data. I guess we can even add that to here, units of original data. Now that we've seen an example where the variance does not have units of the original data, it makes a little more sense to point that out as a pro. And for salary, max of salary minus min of salary, $75,000. So we saw these last time. What about the variance and standard deviation? Remember, Ashley and Brandon are populations, salary is a sample. That hasn't really affected our calculations to this point. Maybe the way that we describe it, or maybe the notation we use might be a little different in some cases, but the actual computation, the mathematics that we do was the same. But for variance and standard deviation, it's not. Excel is smart enough to know this. So if we look at equals VAR, the variance computation function, we see there are two main ones here, var.p and var.s. So they're adopting this function method kind of syntax that's popular with things like Python and so on. where you put it, you have an idea that's like variance. I want to compute the variance, and then kind of like a sub idea, like dot P, I want to compute the population variance or the dot S sample variance. Ashley and Brandon are populations, so since we're looking to compute the Ashley uh, variance, this is a population variance, VAR dot P. And we can see the little note here says calculates variance based on entire population. Whereas if we type dot S, estimates variance based on a sample. So if you forget which one's which, even though it's kind of pretty obvious with P and S, the little note will remind you. So var.p, and then what data set do I want? I want the Ashley data. And we see our variance of 4 for Ashley. That's what we found here. We need to be smart enough to know that this has wonky units. Excel is not going to tell us that. Similarly for the Brandon data, var.p, population again, we said the Brandon data is population. Brandon's variance 16, again in wonky units. The salary data is a sample, so we better be careful. var.s for sample variance, salary. And there we got our 759, just like we got by hand. To go from variance standard deviation, we can either just square root, that's the function sqrt, returns the square root of a number, and I can square root cell B15 to get Ashley's standard deviation of 2, and we're back in normal units now, 2 returns per day. Where was she? Here we go, 2 returns per day. Or we could do equals stdev. And again, we see, I mean, there's a whole bunch of, really off the wall functions down here, but we see the main two, stdev.p or .s. So .p calculates standard deviation based on the entire population. It's exactly what we want. Standard deviation of the Ashley population. And that also gives me 2. Same with Brandon, equals stdev.p for population. Standard deviation of the Brandon data, 4 returns per day. Again, back in units of the original data, back in normal units, just like we saw over here. But again, we have to know enough about stats to know that Excel is not going to tell us what units it's in. And then for the salary data, stdev dot, well, this is a sample. We know because we're told it's a sample dot s of the salary data. And that gives us our about 27.5 or so standard deviation. As a little aside, if you want to make these numbers look a little nicer, if you are on your home tab up here, like home, insert, draw, if you're on home, which is where it kind of defaults to, if you look up in kind of the middle here where it says number, you see like general, you can change it to dollars, you can change it to percents. There's these 2 things that have like a bunch of zeros and like a left or right arrow. If you want an extra decimal place, if you want more decimal places to show in your result, you can hit the blue arrow to the left one that says increase decimal. Or if you want right, if you hit the other one going to the right, you can decrease the decimals. And it'll do the rounding for you. So we can decrease it to like 1 decimal place just by hitting that right arrow a bunch of times. Get it down to 27.5. It looks a little nicer that way. You can also use the round function in Excel, but just using this little, left or right arrow up here is a nice way to adjust it to the number of decimal places you want to see, and it takes care of the rounding for you. Any questions so far? So here for this variance, I got 759. I'm just going to hard code it in right next to that, and 27.5 for the standard deviation. Don't know why that's in bold. So these were the numbers we got as it stands now. What if I take this outlier, this 100, and pop it kind of more into the middle of the data? What if I bring it down to like, say, 40? Changing that one outlier out of 7 points, drop my variance from, say, 700 something to 100 something, drop my standard deviation from 27 down to 10. It cut my standard deviation by a factor of 3 by just changing that one outlier. Even if I made this still the highest number, but coming from 100 down to say 60, it's still it's still a double what most of the data is. We probably would still even maybe call it an outlier. But even then I see that my variance has been cut by a factor of more than 3. My standard deviation has been cut by a factor of right around 2. This one outlier is responsible for a large chunk of this variance to standard deviation. Right, again, I can see if I put it right here in the middle, let's say like 28, my standard deviation is cut by a factor of 3, just from that one data point out of 7 being an outlier versus being kind of in the mix with most of the other data. Or the variance is cut by, a factor of 7 or so. So we see really clearly here with a little bit of simulation in Excel. That's one of the really nice things about coding this into Excel. You can play around with things, see how different things would change pretty easily. We really see that drastic effect of outliers on variance and deviation. I'm not going to see the same thing if I, take Ashley's 7 and make it 8.5 or something. Let's forget that these are full returns completed per day, but if I popped it from below 8 to a little bit above 8, my variance standard deviation 4 and 2, then it's still about 4 and 2, right? Or even if I took the 7 and made it say a 10, still about 4 and 2, right? I'm not changing by a factor of 2 or a factor of 3 or something. It's really the outlier nature that's causing this huge jump in variance standard deviation. If I take this 11 and make it say a 16, then all of a sudden, here we have a pretty clear outlier. It's like twice as big as, all the other data points values. We did have a big jump in variance standard deviation from 4 and 2 to 14 and 4. So because of the fact that we're squaring these deviations, outliers, they have a bigger deviation, then we square it, it becomes a lot bigger. And they disproportionately affect variance standard deviation. Okay, let me switch my share. Let's just keep this up because we'll want to come over here and do coefficient of variation in just a minute. So keep the share about the same. So coefficient of variation, usually just referred to as CV, this is a measure of variation that has the goal of being unitless. It's a measure of variation, so when my data is more variable, I want this number to be higher. I want it to kind of track with like range, variance, standard deviation, something like that. My coefficient of variation is going to be the standard deviation divided by the mean. Or so that would be for a population, or coefficient of variation would be the sample standard deviation divided by the sample mean. Computed the same way in either case. We see it's a measure of variation because the higher the standard deviation gets, the higher the measure of variation gets, the larger the coefficient of variation gets. But two really nice things. One is, well, my numerator standard deviation is in units of the original data. My denominator mean is in units of original data. My units cancel. This is unitless. That makes comparing between different data sets much easier, much more reasonable. It's a unitless number. And the second thing is we've kind of scaled out the size of the data. We can actually think of a data set almost as having like an implicit unit that's like the size of the data in some sense, right? Like if I measure the amount of money that I have in my bank account, if I measure it in terms of how many $100 bills is it, or how many dollars, or how many cents, I mean, I'm measuring the same amount of money that I have, but kind of the size of the data looks very different because I'm using different scales, different units. But also if I measure like how many tax returns does somebody complete per day, and one person works in a, um, whatever, like an office doing big, complicated corporate tax returns, and they can complete, one or two a day, and another person works in, an office doing just general, residential tax returns, and they can do 20 a day because they're just less complicated. Maybe we still have units of returns per day, but these are clearly on a different scale. So there's kind of this inherent size of the data that's going to be reflected in the standard deviation, right? Somebody who only does one or two returns per day is going to have a standard deviation number that's much smaller than somebody who does 20 returns per day, not really because their performance varies so much, but uh, just because the numbers of returns that they're looking at is so much smaller. So by scaling by the mean, by say the average number of returns each person looks at per day, that also kind of scales out this maybe something like an inherent unit, the size of the data. Not talking about the size of the data set, not talking about n, but just like, for instance, how many returns does a person tend to see per day? A person who just completes a lot of simple returns per day is going to look like they have a higher variance of standard deviation compared to somebody who does more complex returns and gets fewer done per day. But that doesn't necessarily mean their performance is much more variable. So by dividing by the mean, we scale out the unit, the explicit unit, but also this kind of implicit unit of like the size of the data set. Okay, so what is the coefficient of variation? Super simple to compute over here. We want Excel to compute something, we type equals, and we just do standard deviation divided by the mean. So 0.25 for Ashley. Then we can just click and drag across to get the coefficient of variation for Brandon, 0.5, and for the salary data, 0.65 or so. Or if we wanted to, we could make this look a little better. Maybe we'll stop there, 0.66. And the nice thing is, since we scaled out kind of the unit and the inherent size of the data values, we can kind of compare these three directly with one another. I definitely wouldn't want to compare these directly with one another. These two maybe not so bad, but these three have different explicit units and different sizes of the data values. But these three, we've scaled a lot of that out. So we can see that kind of inherently the salary data seems to be more variable than the Brandon data, which is more variable than the Ashley data. Any questions so far? Okay, so the range rule of thumb, we notice that the range is easy to compute, but has some drawbacks. The standard deviation is kind of like, maybe something like a gold standard, but is quite challenging to compute, at least by hand. We have a range rule of thumb that the range is approximately 4 standard deviations, or that a standard deviation is approximately 1/4 of the range. So a data set kind of typically takes up a swath of the real line that is 4 times its standard deviation. Or kind of in other words, if I think of a chunk of the real line, representing 4 standard deviations, and I kind of think of my mean being like in the middle here, I might think that I can make a statement something along the lines of typically a data value isn't likely to be more than 2 standard deviations away from the mean. So this is kind of an answer to that question. How far can a data value reasonably deviate from the mean? Yeah, maybe about 2 standard deviations. Now, importantly, this is a rule of thumb. This works quite nicely in some situations and quite terribly in other situations, which is how rules of thumb or heuristics are. That's why it's not a theorem. It's something that often works pretty nicely, but sometimes fails terribly. But there are a lot of ideas that are built on this kind of general concept here that we would typically expect to see most data values or most data points values within 2 standard deviations of the mean. Let me switch my share back. Just going to try to zoom out, but I figured that would make it probably quite hard for you to see, especially if you're on a phone or tablet or something. So the empirical normal rule, we can say something that is a little bit like the range rule of thumb, or like our conclusion from the range rule of thumb, but we can say it much more accurately if we have a constraint on what the data set can look like. If a data set is approximately bell-shaped, if it has this kind of bell-shaped or normal distribution shape, then we can say the following, that approximately 68% of the data points have a value within 1 standard deviation of the mean. So that means if I look at my real line and I put the mean down here as an anchor, I'm using population notation, but we could say the same for sample. And I consider a bar that is with 1 standard deviation. This would be mu plus 1 sigma, and this would be mu minus 1 sigma. So having a value within 1 standard deviation of the mean means that you are in this interval. If I look at a data set that's approximately bell-shaped, and I ask, some of those data values are going to be within 1 standard deviation of the mean, they're going to be in this interval, mu minus sigma to mu plus sigma, and some will be without this interval. And I ask what proportion of my data points have a value within this interval, I'd expect it to be about 68%, about 2/3. If I go out another standard deviation to mu plus 2 sigma and mu minus 2 sigma, all of these values on the real line are within 2 standard deviations, within 2 sigma of mu. If I look at my data set and I do the same analysis, I say some of my data points have value that's within this interval, mu minus 2 sigma to mu plus 2 sigma, and some have a value outside of that interval. What proportion of my data points in an approximately bell-shaped data set have a value within 2 standard deviations of the mean? That's going to be about 95%. And doing this one in red, not for any particular reason, just because that's the color I have left over. Mu minus 3 sigma to mu plus 3 sigma. That is an interval on the real line, a wider interval still. Again, some data points are going to have a value in this interval, some outside the interval. what proportion in an approximately bell-shaped data set should be within the interval. That's about 99.7% or about 299 out of 300. Or another way to look at it is sometimes we talk about it, a data point being a, say, 1 sigma event or a 2 sigma event. That's the kind of converse of this. That when I say a data point is a 1 sigma event, I mean that it's more than 1 standard deviation away from the mean. About 2/3 of our data points will be within 1 standard deviation of the mean. So about 1/3 will be outside of that, will be more than 1 standard deviation from the mean. About 95% or 19/20ths of our data points will be within 2 standard deviations of the mean. So about 1/20th or about 5% will be 2 sigma events, more than 2 standard deviations away from the mean. And about 99.7% or about 299 out of 300 data points will be within 3 standard deviations of the mean. Means a 3 sigma event happens about 1 out of every 300 times. We can see going from 1 to 2 to 3 standard deviations, the rarity increases substantially because this function here, that's kind of an e to the minus x squared function, this goes to 0 very, very quickly. So the chance that I have, say a 3 sigma event that I'm way out in one of these tails is quite small. It's quite unlikely to happen for a bell-shaped data set. All right. I think we will finish up Chebyshev's theorem next time. And that'll be the last little bit in section 3.2. And then we'll move into 3.3 next time. I'll also post, in addition to that, that note on why do we divide by n-1. I'll also post a couple of resources, if they're not already up, on Blackboard in the supplemental material folder on section 3.3. So those resources I'll have up. I'll probably just post them right after we end class today. So keep an eye out for those. Does anybody have any questions? I'll stop.